Hey guys, it's Murat Duman here. In this video series, I'm gonna be talking about electromagnetics. Our textbook is Fundamentals of Engineering Electromagnetics. Its writer is David K. Cheng. In this video, I'm aiming to finish with chapter 1, in which there will be given a brief information about the electromagnetic model. And I'm aiming to prelude chapter 2, in which I'll be dealing with vector analysis. I'll be talking about vector addition and subtraction, vector multiplication, and orthogonal coordinate systems. Let's start with chapter 1. It will be more suitable if you call it creating a sense of the electromagnetic model. Let's start chapter 1 and say something about creating a sense of the electromagnetic model. An electromagnetic theory can be built on a suitably chosen electromagnetic model, and we will do this in 3 steps. First step is defining the basic quantities of electromagnetics. Second step is defining the rules of operation such as vector algebra, vector calculus, and partial differential equations. And third step is studying the fundamental postulates such as static electric fields, static magnetic fields, and electromagnetic fields. The most basic quantity in electromagnetics is the electric charge. It is denoted by lowercase q or capital Q. Electric charge is a fundamental property in electromagnetics and can be exist in nature just positive or negative multiples of the charge on an electron, which is equal to 1.6 times 10 to the minus 19 coulombs. And coulomb is the unit of electric charge in electromagnetics. There are 2 kinds of quantities in electromagnetics: source quantities and field quantities. I will use EM letters for the abbreviation of electromagnetics. Source quantities are the charges which are at rest or in motion. An electromagnetic field may cause a redistribution of charges, and in turn charges may reshape the field, so the separation between the cause and effect is not always so distinct. There are 3 kinds of charge distribution in electromagnetics that we will use in our calculations. First one is volume charge density. It is denoted by rho sub v. Rho sub v is equal to limit as delta v goes to 0 delta q over delta v, which is infinitesimal charge over infinitesimal volume, and its unit is coulomb over meter cube. Second kind of charge density is surface charge density. It is denoted by rho sub s, and rho s is equal to limit as delta s goes to 0 delta q over delta s, which is infinitesimal charge over infinitesimal surface, and its unit is coulomb over meter square. And third kind of charge density is line charge density, and it is denoted by rho sub L, and rho sub L is equal to limit as delta L goes to 0 delta Q over delta L, which is infinitesimal charge over infinitesimal line, and its unit is coulomb over meter. Chapter 2 Vector Analysis. As I said before, vector analysis consists of three topics: vector algebra, orthogonal coordinate systems, and vector calculus. Vector algebra is the first part of vector analysis, and under vector algebra we will study addition, subtraction, and multiplication of vectors. Orthogonal coordinate systems is the second part of vector analysis, and under this topic we will study Cartesian, cylindrical, and spherical coordinate systems. Vector calculus is the third part of vector analysis, and under this topic we will study differentiation and integration of vectors, gradient, divergence and curl operations, and also we will prove two null identities. Let's start with vector algebra and first study vector addition and subtraction. We will demonstrate a vector as a letter over a bar. Every vector has a direction and a magnitude. Direction of a vector in our course will be demonstrated by lowercase a sub the letter which we use to demonstrate the vector, which is capital A in our example. And there will be a cap over this combination. This combination is also a vector with a unit magnitude. It is called unit vector. And in our example, unit vector is in the direction of vector A. And magnitude of a vector is demonstrated after unit vector representation, and it is demonstrated by a letter which is used to demonstrate the vector, which is capital A in our example. Magnitude of the vector. Another representation of magnitude of vector is absolute value of vector. As I said before, absolute value of a unit vector is equal to 1. As it is seen from our vector representation, unit vector is equal to vector over its magnitude. And it is important to note that two vectors are equal if they have the same magnitude and same direction, even though they may be displaced in space. We can add two vectors by the head of vector A connects to the tail of vector B. That is how to get vector A plus vector B. We see vectors A and B here. So we add two vectors by the head of vector A connects to the tail of vector B, and then by connecting the tail of vector A to the head of vector B, we get vector A plus vector B here. And when it comes to subtraction of two vectors, we take first vector as it is. In our example, it is vector A. And then we change the direction of second vector due to subtraction operation. And then by adding these two vectors, we get vector A minus vector B. Let's study vector multiplication, and first of all let's study vector multiplication by a scalar. We are asking the question how to multiply a scalar by a vector. And this is our representation of a vector by its direction and magnitude. When it comes to multiply the scalar k by vector A, the scalar k will be multiplied by the magnitude of the vector A, and the direction will be same of the vector A. Let's continue with multiplication of vectors. There are two kinds of multiplication for vectors. First one is scalar or dot product of vectors, and the second one is vector or cross product of vectors. Let's continue with scalar or dot product. Dot product of two vectors A and B is defined as the magnitude of vector A times the magnitude of vector B times cosine theta. Theta is the smaller angle between vector A and B. This bold point represents the dot product operation. And this sign represents the equal by definition statement. And as I said, this angle theta is the smaller angle between the vectors A and B. Then naturally this question comes to mind: what is the physical meaning of dot product? As it is seen from this figure, the physical meaning of dot product is the projection of a vector on another vector. Vector B projects on vector A this much. Let's write it down. The physical meaning of dot product operation is the projection of a vector on another vector. And one important note is the result of dot product operation is a scalar. Let's talk about some properties of dot product operation. We can simply prove these equations by using dot product operation. As it is seen from first equation, order of vectors in a dot product operation is not important. And second equation says that we can find the magnitude of a vector by using the dot product of itself. And third equation is the another representation of second equation. Second kind of vector multiplication is vector or cross product. Given two vectors A and B, cross product operation is demonstrated by this sign. The cross product of these two vectors is equal by definition magnitude of vector A times magnitude of vector B times sine theta. Theta is the smaller angle between vectors A and B. The result of cross product operation is a vector, so the result must have a direction. The unit vector that belongs to the cross product operation is denoted by A sub n. And n represents the word normal here. And next question is, what is the direction of unit normal vector A sub n? The direction of unit normal vector A sub n follows that of the thumb of a right hand when the fingers rotate from A to B. So, direction of unit normal vector on this figure is upwards. This rule is called as the right hand rule. If we are looking for B cross A, again using right hand rule, by rotating B to A, the thumb of the right hand is pointing downwards this time. So A cross B is equal to minus B cross A. Let's write the definition of unit normal vector A sub n. A sub n is unit normal vector which is perpendicular to the plane containing vector A and vector B. So for A cross B, the unit normal vector A sub n is obtained by the right-hand rule by rotating from A to B and observing the direction of the thumb. And magnitude of the resulting vector is equal to the area of the parallelogram, which is equal to magnitude of the vector A times magnitude of the vector B times sine theta, and theta is the smaller angle between vectors A and B. And naturally this question comes to mind: what is the physical meaning of cross product? The physical meaning of cross product is observing the vortex which is created by vector A and vector B. Let's explain this on an example. For example, on a flat water surface, these are my x, y, and z coordinates. Let's say by using a stick in a very small instant of time, first I draw a line in the direction of x, and then I draw a line in the direction of y. Let's say these are vectors A and B. And then my action will create a vortex, and ring-shaped water circles are getting bigger in area in the direction of Z and perpendicular to the surface containing my drawings in the direction of X and in the direction of Y. Let's write this down. The physical meaning of the cross product is observing the vortex which is created by vectors A and B. And the area of the vortex is getting bigger in the direction which is perpendicular to the surface containing vectors A and B. Let's continue with orthogonal coordinate systems. In electromagnetism, solution of practical problems requires that the relations derived from these laws be expressed in a coordinate system appropriate to the geometry of the given problems. For example, the most basic coordinate system is Cartesian coordinates containing x, y, and z. These three surfaces are mutually perpendicular to one another. We have an orthogonal coordinate system. Most common and useful coordinate systems are Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Let's study Cartesian coordinates. A point P whose components are x1, y1 and z1 in Cartesian coordinates is the intersection of three planes: x is equal to x1, y is equal to y1 and z is equal to z1. We have u1, u2, u3 and they are equal to x, y and z. These u1, u2 and u3 are kind of the general names of the coordinates. For example, for Cartesian coordinates, they are x, y and z respectively. For cylindrical coordinates, they are r, phi and z respectively. And for spherical coordinates, they are capital R, theta and phi. These are base vectors which are perpendicular to each other in Cartesian coordinate system. For a right-handed system, we have the following cyclic properties. For the cross product operation, ax cross ay is equal to az and az cross ax is equal to ay. For the inverse direction, for example, az cross ay is equal to minus ax. For the inverse direction of cross product operation, there comes a minus sign. Since perpendicular vectors has zero projection on one another, and since a vector has full projection on itself, let's say this point is origin and this is a random point P and its coordinates are x1, y1 and z1. The position vector to the point P whose coordinates are x1, y1 and z1 is the vector drawn from the origin to the point P. This vector is demonstrated by O and P points. O is the starting point and P is the end point. This position vector has three components and they are in the direction of ax, ay and az. And their magnitudes are x1, y1 and z1 respectively. This is how to represent a position vector in Cartesian coordinates. The expression for differential length in Cartesian coordinate is differential length has three components in the direction of ax, ay and az. Since we are talking about differential length, all three components has infinitesimal lengths, which are dx, dy and dz respectively. For differential volume element, since we are expecting to find a scalar dV, which represents the differential volume element, is equal to dx times dy times dz. dx, dy and dz are infinitesimal lengths, and multiplication of three of them gives us the differential volume element. Let's see another representation of a vector in Cartesian coordinates. It has three components, as we know, and we see a different representation of vector components for magnitudes here. And this representation for the magnitude says us this is the magnitude component on the x direction. And similarly, this is the magnitude component on the y direction, and this is the magnitude component on the z direction. Let's see dot product of two vectors a and b by using this vector representation. Since these unit vectors are perpendicular to each other, dot product of two unit vectors only gives the result 1 when the unit vectors are same. Otherwise, the result is 0. So, again, by using this vector representation, cross product of two vectors a and b is Actually, these results make sense, since the cross product of y and z components gives rise to a component in the x direction. And if you change the order of the vectors in the cross product operation, there comes a minus sign. And same thing is valid for the other components. And cross products can be conveniently written in a determinant form. And let's solve some examples. First example, we are given vector A in Cartesian coordinates, and first we are asked to find its magnitude. We know that dot product of a vector with itself gives the magnitude square. So, and magnitude of vector A is equal to root square 9 and it is equal to 3. This is part A. In part B, we are asked to find the unit vector in the direction of vector A. We know that unit vector is equal to vector over its magnitude. So, magnitude of vector A is equal to 3 and vector A is and this is the unit vector in the direction of vector A. In part C, we are asked to find the angle that vector A makes with the z-axis. Let's remember the equation for dot product operation. And for vector B, let's take the unit vector in the z direction. We use this notation in order to state that this angle is between vector A and z-axis. Let's continue to dot product operation. Magnitude of vector A is equal to 3, and from here minus 2 is equal to 3 cosine theta z, and theta z is equal to arc cosine minus 2 over 3, and from here theta is equal to 131.8 degrees. And in part D, we are asked to find the component of vector A in the direction of vector B. The component of vector A in the direction of vector B is equal to dot product of vector A and the unit vector in the direction of B. Vector A is equal to if you calculate unit vector in the direction of vector B as it is calculated in part A, you will find out that it is equal to so the component of vector A in the direction of vector B is equal to minus 20 over 7. Example 2. Let's go step by step. Write the expression of the vector going from point P1 to point P2 in Cartesian coordinates. In other words, we are asked to write the expression that belongs to this vector in Cartesian coordinates. Our starting point is P1 and our end point is P2, so we're asked to write the expression of this vector. In order to understand how to write the expression that belongs to this vector, let's examine a simple example. Let's say this is origin and this is vector P1 and it is equal to unit vector in the direction of x, and this is vector P2 and it is equal to unit vector which is in the direction of minus x. As this seen from here, our starting point is P1 and our end point is P2, so as this seen from the figure, our starting point is P1 and our end point is P2. So vector P1, P2 is in the direction of minus x and its magnitude is equal to 2. By investigating this simple example, we see that vector P1, P2 is equal to vector OP2 minus vector OP1. And O represents the origin here. Let's turn back to our example. Vector P1, P2 is equal to vector OP2 minus vector OP1. Vector OP2 is equal to and vector OP1 is equal to and the result is and this result belongs to vector P1, P2. This is part A. And in part B, we're asked to find the magnitude of vector P1, P2. In order to find magnitude of a vector, we use this equation. We know how to use this equation since we used this equation in the first example. I will directly write the answer. In part C, we're asked to find the perpendicular distance from the origin to vector P1, P2. So we are asked to find the magnitude that belongs to this vector. Magnitude of vector ON is equal to magnitude of vector OP2 times sine alpha. Since we are trying to reach sine alpha, we can try to get this term by using cross product operation. This term is equal to absolute value of the cross product of vector OP2 and the unit vector in the direction of vector P1, P2. This unit vector is equal to vector P1, P2 over its magnitude. So vector ON is equal to vector OP2 is equal to and vector P1, P2 is equal to and the magnitude of vector P1, P2 is equal to root square of 33. And the cross product operation is equal to and the result is 3.4. This is the magnitude of vector ON. Example 3. Given 2 points P1 and P2, find the length of the line joining P1 and P2. Let's go step by step. Let's say this is origin, this is point P1, this is point P2. This is vector OP1 and this is vector OP2. And this is the line joining P1 and P2, which is vector P1, P2. Vector OP1 is equal to and vector OP2 is equal to vector P1, P2 is equal to vector OP2 minus vector OP1, and it is equal to and the magnitude of vector P1, P2 is equal to 6, and this is part A. And in part B we are asked the perpendicular distance from the point P3 to the line which connects the points P1 and P2. Let's say this is point P3 and this is the perpendicular distance that we asked for, and let's say this point is K and this is the vector, let's say P3K. So we are asked to find the magnitude of the vector P3K. Let's say this is vector P3, P1, and this is the angle between the vectors P3, P1 and P1, P2. So the magnitude of vector P3K is equal to the magnitude of vector P3, P1 times sine alpha. And this is equal to absolute value of cross product vector P3, P1 and unit vector P1, P2. Unit vector P1, P2 is equal to vector P1, P2 over the magnitude of vector P1, P2. So we are asked to find and the magnitude of vector P1, P2 is found as 6 in part A. So we are trying to find let's find the result of this cross product operation. We will find the result of this cross product operation by using the determinant form. And magnitude of this vector is equal to 27.2, so the result is 27.2 over 6 and it is equal to 4.53. This is the magnitude that we asked for. Example 4. Given vector A, find the expression of part A unit vector in the direction of vector B such that unit vector is parallel to vector A. Let's go step by step. If unit vector in the direction of B is parallel to vector A, then the cross product of this unit vector and vector A is equal to 0. And we can represent this unit vector as since this is a unit vector, summation of the second power of all its components is equal to 1. Let's write it down. Let's look at the cross product operation. Since the result of this cross product operation is equal to 0, all these individual summation and subtraction operations must be equal to 0. So if b sub z is equal to, let's say, the constant k, then b sub y is equal to minus 2k. If b sub y is equal to minus 2k, then b sub x is equal to 5k. And by using this equation we can write this. By using this magnitude, we can write the unit vector in this form. Then the unit vector that we look for is this was port A, and in port B, vector A is equal to and this unit vector is perpendicular to vector A, and this unit vector is in the xy plane, and we are asked to find this unit vector. Since this unit vector is in the xy plane, z component is equal to 0, so we can represent this vector, this unit vector, as since this is a unit vector, summation of the second power of all its components is equal to 1. So and since this unit vector is perpendicular to vector A, their dot product is equal to 0. So let's say this is equation star and this is equation double star. Let's put equation double star in equation star. So by using equation double star, then the unit vector that we look for is example 5. Decompose vector A into two components, vector A1 and vector A2, that are respectively perpendicular and parallel to another vector B. Let's say vector A1 is a part of vector A and it is perpendicular to vector B. Then dot product of vector A1 and vector B is equal to 0. And in the same way, vector A2 is part of vector A and it is parallel to vector B, then the cross product of vector A2 and vector B is equal to 0. And the summation of vector A1 and vector A2 is equal to vector A, which is equal to and vector B is given as we can write vector A1 as and can write vector A2 as let's look at the cross product of vector A1 and vector B. And from this equation we can write this. Let's say this term is equal to constant m, then this term will be equal to 4m. And we have no information about the z component of vector A1. Let's look at the cross product of vector A2 and vector B. Since this vector is equal to 0, all three components are equal to 0, so this term is equal to 0. Now we know that the z component of vector A2 is equal to 0, and at the same time we know that summation of vector A1 and vector A2 is equal to vector A. Then summation of the z components of vector A1 and vector A2 is equal to 3. And we know that the z component of vector A2 is equal to 0. Then the z component of A1 is not an unknown for us anymore, and it is equal to 3. And also this term is equal to 0. If this term is equal to k, then this term is equal to minus 4k. If we use this information, vector A1 is equal to and if we use this information, vector A2 is equal to and we know that addition of vectors A1 and A2 is equal to vector A, and it is equal to and by using this information we can write this addition as and it is equal to vector A. And from here we know that 4m plus k is equal to 2 and m minus 4k is equal to minus 5. So 4m plus k is equal to 2 and m minus 4k is equal to minus 5. And from here m is equal to 3 over 17 and k is equal to 22 over 17. Now by using these numbers we can write the exact vectors a1 and a2. So vector a1 is equal to and vector a2 is equal to So we are finished with this example. Now, independent of these examples, I will write an equality about cross product operation as a node, which is a vector triple product, and it is and this equation is also known as the back-cap rule. You can prove this equality by using cross-product operation, and I want you to memorize this equality because we'll use this equality in the future lectures and future examples. Today my aim was to be finished with orthogonal coordinate systems, but it has been almost an hour. And for the sake of efficiency, I try to set lecture duration as an hour. So for the next video, I'll continue with cylindrical coordinate system. If you like this video, don't forget to subscribe. See you.